Hello world. Uh, in this paper or a presentation of a paper, we are going to look at Chord, which is a very beautiful implementation of a distributed hash table. And it's a foundation paper for a lot of the distributed systems which we build today. Um, Moving on, we have as an overview, I'll look at what Chord is, how it uses consistent hashing, some of the related work before Chord, or how Chord could improve those work. So we'll look at the architecture of the Chord protocol, which it has for maintaining the invariant, and some of the results shared from the paper, and of course the some of the notable work based on Chord we'll look at as well. So Chord is a P2P lookup protocol which implements consistent hashing, based distributed hash table. And but the goal of the Chord is very simple. It For a given key, it maps onto a physical node or a virtual node. So it doesn't care about how the data is stored. That responsibility is on the client or the user. Chord only takes care of mapping a key onto a physical node or a virtual node. Here on, when I mention node, I'll just mean it's a physical node for simplicity. So, however, the data location can be easily implemented on top of Chord by associating a key with each data item, right? And storing the key data pair at the node to which the key maps. So once the location of the node has been identified, the exact location of data can be retrieved from the target node. The data here could be address, like in case of DNS, the address is the IP address for a host name, a document, or an arbitrary data item. Chord scales horizontally, and we'll see very shortly. It maintains a routing table, and that the size of the routing table is logarithmic to the size of the node, I mean, number of nodes in the cluster. The lookup resolves in log n hop, which is again really good. Uh, and some of the ideas of the of why it is important is we'll discuss when we look into the architecture of the Chord or related work in the protocol as well. Chord is fault tolerant. It handles node failure and joining of the new nodes, and this is very critical. Which will look at how these ideas were not supported in a typical hash table. How consistent hashing helps provide more practical implementation of hash table in a scenario where nodes fail all the time. So in a traditional hash table, the way we build a hash table, any hash table, whether it is universal hash function, or for even a perfect hashing, right? We have to define the size of the hash table upfront, right? And when the size of the hash table changes, for whatever reasons, uh, we need to remap the keys again, right? But in practice, when we are building a distributed hash table, this is very difficult, right? Requirement, because nodes fail very often, right? So that means, and nodes join as well. So that means the size of the table would change very often, right? And since they store a lot of the keys, it's not just possible to map the keys again, right? Because what happens to the cluster? Would the cluster be operational while the keys are being remapped? So it's a very challenging task. So as a workaround to that, we we have a very beautiful design called consistent hashing, which maps a key onto a circular ring in a clockwise fashion. So let's say instead of a hash table of slot size m, we could imagine the ring to hold all the values, from 0 to 2 power m in a clockwise fashion, right? Each of these values or the identifier on the ring could represent a key as well as a node. Node being the server, physical node or the virtual node, does not matter. So The key idea about the hashing is consistent hashing is each node is responsible for storing key only in a certain range. So any node failure or joining does not cause disruption in other part of a cluster. That's very important. And I'll expand on this idea a bit more when I show how Chord uses consistent hashing to map a key onto a node in a Chord ring, which is nothing but a circular ring. So as a summary, the main takeaway from the consistent hashing and how it is better than the traditional hash table is the key movement is very low in case of node joining or leaving the cluster. Some of the related work we look at is DNS, which is a hierarchy of special root servers. It has a namespace server as well. Chord, on the other hand, is a very flat hierarchy. It can support a DNS lookup as well, where we have a given host name, we map it to a key. Freenet, on the other hand, follows a tree-like structure where a lookup for a key traverses a path, and once the target node is found, the path is retraced, and while the path is retraced, the intermediate nodes will cache the key. So any subsequent lookup will be retrieved from the cached copies, and that's how it provides the anonymity. However, it does not provide a low bound on the retrieval cost, which the Chord provides, a very good predictable log and retrieval cost. Tapestry is very similar to Chord. However, it's complicated in terms of the protocol to handle the node failure and the node joining. It's critical that the system is not just more efficient but also simple to implement, right? So Chord shines in those points. Napster and Nutella. Napster is a very simple index server. In a original design, there was only single index server, which is a single point of failure. However, later the authors, had more index servers. But the problem is the clients still have to go through the index server to retrieve a key. It's a very typical master-slave architecture, which has a bottleneck of master. Nutella, on the other hand, uses a gossip protocol, which is a very simple gossip. Whenever a node receives a data, it gossips the information to few other nodes, and every node does the same, and that's how the gossip spreads very fast, right? However, the problem is the communication cost. It's pretty high because every node is sending data to every other node, and not just single node, but few other nodes. On the other hand, in Chord, there's no single point of failure like Napster, or there's no heavy communication cost because every node is responsible for key in a certain range. So any node joining or failure affects only the nodes in that particular region of the cluster and not the entire cluster. So the architecture of the Chord is pretty simple. It simplifies some of the key idea of a P2P system. It has a load balancing with SHA-1 hash function. This where hash table spreads the key evenly over the nodes. Um, it's scalable because there's no parameter tuning required. Uh, like some of the storage system which we have today, HDFS and Ceph and and bunch more, they require a lot of parameter tuning upfront. If you need like a really take the performance out of them. Uh, they are decentralized. There's no single point of failure, like unlike HDFS, for example, which has a name node server, which is again follows master slave architecture. Availability, bearing a major failure like network partition and so on. Nodes are always the key for the node are always found. Flexible naming, which is very important. Chord does not impose any restrictions on the hierarchy of the key like DNS has. That if you look at IPv4 structure, it follows a very strict domain order namespace, right? And that's how it is resolved. But no, Chord does not have any such restrictions. It has a flat key space, and it lets the application figure out how to map their own keys to the Chord key. So this is the chord ring structure. The green ones are the nodes. The one in the box are the key, which we are storing. How the keys are mapped to the node, I'll explain shortly. But look at the structure. The key takeaway here is that the node identifier wraps over the largest node. Uh, you know, uh, so it follows a circular ring-like structure. Any node is responsible for storing the key in a range. So node N21 would be responsible for storing a key between N14 and N21, and N32 would be responsible for storing key between N21 and N32. So you could see here key 24 and 30 are mapped to node 32. Another key observation here is that the key need not be mapped directly to the node. The node may not be present on the ring for that key. So the keys are mapped onto a node which follows immediately after that key in the identifier ring. So some of the protocols of Chord talk about how to find the key, the location of the node for which stores that key, or the metadata for that key, which we may be interested in. So all the resolution has to first figure out where the key is located, and then the corresponding data retrieval could happen. How new nodes join the system, and how the system recovers from a failure. Finding a key. So in Chord, the authors have chosen SHA-1 as a base hash function. However, they mention users are free to use their own family of hash function. Particularly, universal hash function would provide more, robust, tolerance of adversary attack. In a SHA-1 based hash function, we have a mbit identifier. Each of the key and the node has an identifier. The key identifier is produced by hashing the original key. Node identifier is chosen by hashing the node IP address. Identifiers are ordered on chord ring, similar to consistent hashing, which we saw earlier. The key is assigned to the first node, like I was saying, first node whose identifier is equal to the node, or the identifier which immediately follows the key in the ring. That identifier is also called the successor of the key, uh, as it follows immediately after the key on the ring. So if you look at the ring structure again, the green ones are the node actually present on the ring, 0, 1, and 3. The one in the box are the key, which we need to map. So key 1, fortunately, it finds a node corresponding to its identifier on the ring. So 1 gets mapped to node 1. However, key 2 does not have a corresponding node on the ring. So it gets mapped to the identifier node, which follows immediately the identifier of the key. In this case, it is node 3. Node 6 again does not exist. So key 6 does not have its corresponding node. So it gets mapped to the node following key 6 in a clockwise direction on the ring, that is node 0. What happens when a new node are added? Let's say we add a node at 7. Will the key in the node 0, the key 6 will be shuffled, will be moved back to node 7. We'll look at those some of the ideas shortly when we talk about what happens when the node joins or leaves the cluster. But for now, the idea is very simple. We have a ring-like structure. Nodes are present on each of those identifier on the ring. It's not necessary that the every node are present on the ring, but more generally the nodes are sparse. And of course, we cannot have a size of the hash table equal to the universe size, right? So more often the ring is sparse. So the keys get mapped to the node which is not equal to their identifier. Each node needs to be aware of only the successor node on the ring. That means every node knows what's the next node is. And so if we want to query a key and the key is not present on the node, that node can query the next node and so on until it passes around the circle. Uh, so this is a very simple design. It's very fault tolerant in a way that as long as every node knows what's the next node is, the query lookup could happen. However, it's a very expensive because it requires a linear, it requires visiting all the nodes in the ring in the worst case. It's a bad design. So to circumvent this issue in a chord structure, each node maintains a finger table. The ith entry in the table contains the ID of the first node that succeeds n by 2 power I minus 1. So every node n maintains a finger table, and the ith entry in the finger table is basically the first node that succeeds n by 2 power I minus 1. That means n plus 2 power I minus 1. Whichever node, the identifier of the node which is more than or equal to n plus 2 power I minus 1 is the successor or the ith entry of that particular node in a finger table. And this is very interesting structure as it makes the finger table logarithmically small. So for a size of n, the finger table is no more than log n. So let's look at this example here. So here we have shown a finger table for a node on the left, and this figure has been taken from the chord paper. So node 8, I mean, for example, the first entry of the node 8 finger table is no 14, because if we do the maths, 8 plus 2 power 1 minus 1, which is 9. So the first node which is greater than 9 is 14, right? So in a simple terms, each of these increments happen in a exponential term. So the next node would be any node which is, the next entry is 8 plus 2, which is 10. So the node which is greater than 10 and immediately follows in a clockwise direction on the circle is node 14. So it means is node 14 stores key from from 8 to 14, right? So all the key that gets mapped between 8 and 14 gets mapped to node 14, right? And so on. So this gap increases exponentially. So we could see after node 14, the next node is node 21 and node 32 and node 42, right? So so the structure of this finger table is such that the nodes which are closer to the key would have more information, right? So if you're doing a lookup for a key which is closer to 8, the node which is 14 would have that information. But if we are doing a lookup for a key which is like 51, then we need to take a jump and reach node 42, because the farther node would have more information about the key than the nodes which are closer. And this is a very key idea of the chord in providing logarithmic lookup time, which says if the key is not available in our node, we redirect it, forward the request to a node which is closest to the key. Okay, and but it has to precede the key. It need not be overshooting. So the things which we have to look at is like I showed, the finger table nodes more about the closer nodes than the nodes further away. So any key successor which we are trying to look at is will ask the node I in the finger table closest to the key. Query then gets forwarded to that node, as that node would have more fine-grained info, and this happens until convergence. How new nodes join the system? Each node maintains a predecessor pointer, and whenever a new node joins the network, certain keys previously assigned to n successor, let's call it n prime, now becomes assigned to n. So that means n, when it joins the cluster, it takes some of the key from its successor and becomes, becomes responsible for that key. We also need to update the predecessor of n, which was like the predecessor of n prime before. So we have to inform the predecessor of n prime that n has become a successor of that predecessor. So it's the idea is similar to linked list. We update the pointer whenever we add a node between two nodes. So recovery from failure is very critical as well. When a node leaves network, either voluntarily, in that case, it assigns its key to its neighbor, both successor and predecessor. The successor and predecessor nodes are informed as well, and that's when they, change their pointer respectively. Each node also maintains a list of R successor in case of network partition or an immediate successor going down. The node can reach out to the next successor in the list and so on. And the probability of R failures is pretty low for P being the probability of a single failure. Periodic run of stabilization protocol in the background to update finger table and successor pointer. So the stabilization protocol asks successor for its predecessor, right? This may be n's new successor because new node would have joined between n and the successor of n, and in that case the node has to update its successor pointer. It also notifies successor of n's existence. So if a new node joins between n and the successor node, n has to also inform the successor of its existence. So successor would update, its predecessor pointer. And this stabilization happens, periodically in a cluster. And the communication is still very low because every node is communicating with its peer. So the results, which we have, which we expect from the design is as the node grows, the number of lookup cost would still be logarithmic. So we could see here a result from the paper. As the number of node grows on x-axis, the path length varies, logarithmically. Lookup path with respect to node failure as well is critical because when nodes fail, we want to ensure that lookup cost does not degrade very rapidly. So we could see on the left side, we have a fraction of failed nodes, 0.1, 10%, 20%, even up to 50%. The mean path length does not degrade drastically. In case of no failure, the path length is 5 hops. Otherwise, it is in case of 50% in the setup, the path length is 8, which is pretty good. So some of the work which are based on Chord, which we'll look at, Cassandra, of course, which borrows ideas from Amazon Dynamo and Google SS table, big table. But however, underlying routing still uses Chord ring-like structure. Coral, which is again a P2P content distribution, geographically distributed network, which has a sloppy concept of a distributed hash table. The figure on the right shows that. So it follows a concentric ring-like structure. The inner ring are, the one with the smaller diameter are more sparse, and the outer ring are more dense. So first the lookup happens in the inner ring, and then the resolution happens in the outer ring. So this way, think of the inner ring as an express highway and the outer ring as a very slow, highway. So the major distance of the network is covered in the lower ring, and then the resolution happens in the subsequent higher rings. It's a very simple design, uh, which is again based on a ring-like chord ring-like structure. Another very interesting application is WebRTC. In WebRTC, the peers need to connect to each other, and to be able to do that, they first reach out to a signaling server, which basically coordinates peer and exchanges session description protocol, which is nothing but just a protocol for peer to establish a session for connection between them. However, the problem is that most well-known signaling method cannot provide the scalability because the method relies on only single server. To overcome the problem, the heart of the protocol is that peers participating in the WebRTC application maintain the structural connections based on a distributed hash table, so that any peers can connect to any other peer using underlying connections, bypassing the central server. This makes WebRTC signaling more reliable and scalable even when a large number of peers are on the network. So this is very critical in a way that the peers still need to reach out to signal server only for the for the initial connection. But however, for discovering the peers which are in that network, the for all the subsequent connections, the node does not have to reach out to signaling server again. So once the node has been added to a cluster, it can discover its peer using this distributed hash table. So it's a very interesting application of Chord. Some of the reference we have looked at is consistent hashing, Chord, Cassandra, Coral, and the WebRTC, you know, signaling, bypassing the signaling server. Thank you.